Okay, great. So thanks again for inviting me. So today I have a feeling that what I'm going to say today might be a little bit, may sound a little bit trivial for the philosophers of physics, but nevertheless, hopefully I'm going to build some intrigue with respect to problems in the philosophy of chemistry, as this is mostly, so from my part, I've been mostly interested in the measurement problem insofar as it kind of helps us resolve and understand chemistry's relation to quantum mechanics. And this is what I'm going to talk about today, is how the measurement problem can be a solution to philosophical problems in chemistry. I have to say before I start that this is in a large part a joint work together with Alexander Franklin. Together we wrote a paper that's currently published in the BJPS, where we talk explicitly about how the measurement problem can solve the so-called problems of molecular structure. But today I will try and kind of present this in a more general way by showing you more generally how the measurement problem can help resolve, can help us understand the identity of molecules, the nature of chemical properties, and ultimately the relation between the two sciences. So obviously, you know much better than I do that quantum mechanics plays a crucial role in describing chemical entities and properties since the past century. And physicists and quantum chemists have done extensive work identifying and resolving the difficulties associated with quantum mechanical descriptions of molecules. However, when it comes to the philosophy of chemistry, there remains still a lot of room to further disseminate these scientific results and include them in the examination of philosophical claims. Now, of course, by this, I do not want to suggest that there hasn't been a very thoughtful and close examination of science and quantum mechanics in particular. However, there is, as I hopefully will show today, a more close examination and explicit examination of the measurement problem and its solutions can help us resolve persistent disagreements around chemistry's relation to quantum mechanics. And this is the goal today. So I want to show how considerations on the measurement problem and its putative solutions can contribute in novel ways to philosophical issues around chemistry, and in particular to our understanding of chemistry's relation to quantum mechanics, but also to our understanding of the nature of molecular structure and of the identity of molecules. Now, the structure of my talk is going to be as follows. First, I'm going to kind of briefly present the story so far. So how has chemistry relation to quantum mechanics been understood in the philosophy of chemistry? And how have philosophers of chemists understood the role of quantum mechanics in this topic? And then I'm going to focus on one specific case study, which has been deemed a peculiar case study with respect to the defense of reduction of chemistry. And this has to do with the molecular structure and how it is identified and described within quantum mechanics. And I'm going to show that the purported evidence against the reduction of chemistry can actually be explained in terms of the measurement problem. And if we do that, then this opens novel ways of understanding chemistry's relation to quantum mechanics in ways actually that haven't been thought so far in the philosophy of chemistry literature, and that more importantly don't necessarily require the rejection of the reduction of chemistry to quantum mechanics. So I'm going to discuss the philosophical implications of considering the measurement problem and its putative solutions, and then I'm going to conclude my talk. So let me go to the story so far. In 1929, Paul Dirac said that the underlying physical laws necessary for the mathematical theory of the whole of chemistry are thus completely known. And the difficulty only lies in the exact application of these laws, in the fact that they are that the equations are much too complicated to be solvable. Now, this is a very much cited quote in the philosophy of chemistry, if you look at how philosophers discuss chemistry's relation to quantum mechanics. And it seems that philosophers of chemistry have been quite intrigued, if not bothered sometimes, by this confident reductionist kind of statement, I suppose, about a century ago. However, at the beginning, this was taken, especially in the philosophy of science, to be kind of a statement of an uncontroversial reduction, right? So, for example, Ernest Nagel in The Structure of Science took that chemistry's relation to quantum mechanics was an uncontroversial example of intertheoretic reduction. However, back in the 1990s, when philosophy of chemistry started to develop as a more rigorous discipline of philosophy, philosophers who were trained in chemistry started to think that this was not so obvious. And they tried to show that reduction is not so obvious by focusing on very specific case studies from chemistry itself. So by looking at the periodic table, or how molecular structure is described in quantum mechanics, or even chemical reaction rates, philosophers of chemists started to identify and show the difficulties, the actual difficulties that exist in supporting a reductive view about chemistry. And it is interesting because this was supported by a more general attitude to kind of defend an anti-reductionist view with respect to chemistry. And it was taken that, you know, the relation between chemistry and quantum mechanics is a very important topic, not only for establishing the autonomy of chemistry, but also for showing the legitimacy of the philosophy of chemistry as a worthwhile field of study. And I've put here the quote by Hasok Chang. I'm not going to read it out loud because I can see my image is blocking the quote, so I cannot see the whole text anymore. But hopefully you can see what he describes as being how important it is to examine the relation between the two sciences, not only for the autonomy of chemistry itself, but also for philosophy of chemistry more generally. And indeed, if we are to look at the literature on chemistry's relation to quantum mechanics, we will find an abundance of anti-reductionist views in this topic. So, for example, Eric Skerry in his initial works on this topic would advocate the failure of the epistemic reduction of chemistry to quantum mechanics. Others would go as far to argue in favor of pluralism, either of the methodological or even of the ontological kind of pluralism. And of course, there are also different types of emergence that have been advocated with respect to chemical entities and properties, most characteristic perhaps being that of Robin Hendry, who argued for the strong emergence of molecular structure, given how molecular structure is described in quantum mechanics. Now, of course, this doesn't mean that there weren't also reductionist views out there. So, for example, Bader's quantum theory of atoms and molecules was purportedly supporting an epistemological reduction of chemistry to quantum mechanics, as his theory would show exactly how you can cash out and describe chemical properties through quantum mechanics. Other philosophers tried also different strategies by accepting the impossibility of epistemological reduction and nevertheless trying to support and advocate the ontological reduction of chemistry to quantum mechanics. And then there are also more modern views of unity that do not imply an eliminativist form of reduction of chemical entities, but nevertheless point out the dependencies that exist between the two sciences. However, it's fair to say that, as Hitima puts it, that the idea of anti-reductionism still is quite popular in the philosophy of chemistry, and that reductionism, on the other hand, is a bit of an unfashionable doctrine in the field. And this is interestingly like a meta kind of a meta comment on this, I suppose, is that this is partially prompted by worries that do not have so much to do with the relation itself and how we perceive it, but rather with other considerations, and in particular with how we perceive the autonomy of chemistry and the legitimacy of the philosophy of chemistry. So it's often even explicitly stated that if we accept reduction, then chemistry turns into a phenomenological science, which has just heuristic value. And that if we do accept reduction, then also we undermine the legitimacy of the philosophy of chemistry, because then chemical examples just turn into mere case studies for more general philosophical problems. So that's a general comment that I just wanted to put out there. But now let's go a little bit more technical and see what kind of evidence do anti-reductionists invoke in order to support that chemistry is not reduced to quantum mechanics. And molecular structure is one of the most standard case studies that is used and invoked in support of anti-reductionism. And it is said that the way in which quantum mechanics identifies the structure of molecules supports the failure of reduction. Now, by molecular structure, let me just put out the definition here. I refer to the shape or geometry of a molecule, so the spatial arrangements of the atoms that constitute a molecule. And molecular structure is one of the most central properties in chemistry because it's used to identify and distinguish between different types of molecular entities, but it is also involved in explanation of chemical reactions and of various physical and chemical phenomena, right? So it's a very important property in chemistry. So anti-reductionists claim that the way quantum mechanics describes molecular structure is kind of peculiar. And this is why, and this is evidence of the fact that chemistry is and cannot be reduced to quantum mechanics. And there are often two problems that are involved in order to show the peculiarity of molecular structure. And the first one is Hund's paradox. So in 1927, Hund formulated a paradox about chiral molecules. Now, chiral molecules are sets of molecules which are comprised of the same number and types of atoms and that are connected to each other in the same way. Nevertheless, the two molecules are not superimposable on their mirror images, right? So there are two molecules the same, but if you turn them around, you cannot impose the mirror image of the one to the other, right? So Hund noticed, and rather chemists, when they refer to these two molecules of a set of chiral molecules, they refer to one as the right-hand side, right-handed enantiomer, and the other one as the left-handed enantiomer. Now, according to Hund, if you were to describe chiral molecules quantum mechanically, you would see that the two enantiomeric structure, neither of the two chiral structures are energy eigenstates of the symmetric Hamiltonian. Instead, the ground state of the molecule corresponds to the symmetric superposition of the two structures. And this is a paradox because even though you see that the ground state does not have definite chirality, what you observe is a molecule with definite chirality, right? Now, there have been various replies to this. For example, Hund himself explained this by the possibly very long tunneling time from the left-handed configuration state to a right-handed one. Also, other scientists have explained this in terms of the environmental decoherence and said that if you take into account interactions with the environment, then you can explain away this paradox. And there are also philosophers who have advocated for a specific interpretation of quantum mechanics in order to explain away the paradox. Now, already you can see here how implicitly the measurement problem crops up, at least in some of these existing replies. But before I talk further about this, let me go to the second peculiarity that's been invoked in the philosophy of chemistry, which has to do with the so-called controversy between resultant and configurational Hamiltonians. So this problem has been formulated in different ways for quite a long time now, but I'm going to present it in terms of Robin Hendry's terminology here. So he distinguishes between two types of Hamiltonians, the so-called resultant Hamiltonian and the configurational Hamiltonian. And he defines the resultant Hamiltonian as the one that takes into account all the physical properties of all the entities that comprise the molecule, down to the level of nuclei and electrons, without making any ad hoc assumptions of how those electrons and how those entities interact with each other, right? And then in contrast to the resultant Hamiltonian, he defines a configurational one as the one that presupposes certain restrictions and assumptions with respect to the particles by registering structural information from chemistry. So unlike the resultant Hamiltonian, which is supposed to be the in-principle way in which you can build up a bottom-up description, a quantum mechanical description of molecules, the configurational Hamiltonian already assumes some information of the structure of the system in order to describe in full the molecule, right? Now, the problem here is that according to Hendry, only the configurational Hamiltonian is used for the description of molecules, and resultant Hamiltonians are not used. So there are two questions here that are revealed. The first is, why aren't resultant Hamiltonians used to describe structure? And how is it that configurational Hamiltonians actually succeed in describing structure? Now, of course, the first question is connected. An answer to the first question partially explains the second question as well. But let me go a little bit into the first one. So why aren't resultant Hamiltonians used to describe structure? Well, it is said that the reason why they aren't used is because they cannot distinguish between different kinds of structures. And this becomes particularly evident if we try through resultant Hamiltonians to describe so-called isomers. So isomers are groups of molecules that are comprised of the same type and number of atoms, yet each molecule is connects those atoms in different ways. So for example, if you have a system consisting of 8 carbon atoms and 8 hydrogen atoms, there are multiple ways in which those atoms can be connected to each other. So it's a very specific set of isomers that one may observe, from styrene, cubane, and all the other ones I've mentioned, you can see here. Now, the problem with resultant Hamiltonians is that when you use the resultant Hamiltonian for that system in order to build the Schrödinger equation, you cannot actually distinguish between the different structures. The respective Schrödinger equation for each one will have the same form. So the resultant Hamiltonian doesn't distinguish those molecules in terms of their structural differences. And this is why, according to Hendry and other philosophers, we do not use resultant Hamiltonians, because they cannot give a the structural differences among the possible structures a specific molecular system can take. Instead, we use configurational Hamiltonians to do that. And why is it that configurational Hamiltonians do manage to distinguish between these isomers? Well, this is in large part due to the so-called Born-Oppenheimer approximation, which already imposes some of the structure that it is said to identify by freezing the nuclei in space, right? Now, of course, in the literature about chemistry's reduction, this is taken as a problem, because the Born-Oppenheimer approximation shows that we cannot actually derive from quantum mechanics and first principles all the information of the chemical system, but we rather need to make ad hoc assumptions about the structure that we are looking for in order to then get a full description of the molecule and its structural properties. And this is why also this has been invoked against reduction. So this is where anti-reductionists say you can see the failure of reduction of chemistry, because the need to make such ad hoc assumptions show that the chemical facts cannot be derivable by quantum mechanics. And this has also been taken as a characteristic instance of emergence. So for example, Robin Hendry claims that the molecular structure downwardly causes, or rather partially determines, how quantum mechanical entities interact within the molecule. And this is because it strongly emerges at a level of ontology that in principle is not identifiable by quantum mechanics. So this is a very strong ontological claim, right? Of course, there are other responses as well that are not necessarily anti-reductionist. So for example, Prima says, well, this is because we have this situation because quantum mechanics is not yet complete, or it might be even false. And then we have also a response that sounds a little bit like trying to connect this problem to the measurement problem, but doesn't get us exactly there, by Eric Skerry, who says, well, this is an instance of the problem of the collapse of the wave function. However, he says this can be completely solved by appeal to decoherence. So it seems we're getting there, connecting the dots and getting to the measurement problem, but not quite, but not completely, right? And now this brings me to the measurement problem. So how does the measurement problem fit in all this? So in our joint paper with Alex, we argue that both Hund's paradox and the use of resultant Hamiltonians are special cases of the measurement problem. And this is supported by two facts. First, both problems have the same form as the measurement problem. And secondly, the three realist mainstream resolutions of the measurement problem can resolve both of them. By this, of course, I do not suggest that the other existing solutions to the measurement problem cannot be equally applied here. It's just that we just, you know, in order to accommodate the space of our paper and to kind of keep ourselves a little bit restricted, we focused on three standard solutions to the measurement problem, but I assume you can also consider other ones as well. So here again, here we use as well Modlin's formulation of the measurement problem that Lev mentioned before. So according to Modlin, the measurement problem amounts to the incompatibility of the three following statements: that the wave function is complete, and it involves in accordance with a linear dynamical evolution, and measurements are always showing a specific a determinate outcome, either spin up or spin down. And there's this incompatibility amounts to the measurement. The incompatibility of the three statements amount to the measurement problem. So we assume this formulation of the measurement problem in order to show that the two cases are actually special instances of the measurement problem as well. And let me be a little bit more specific here. So in the case of, let me just 1 moment, sorry about that. Yes, so let me be a little bit more specific here. So in the case of Hund's paradox, I think it's quite clear that this is a special case of the measurement problem because all three statements in Modlin's trilemma are satisfied. So the most stable state of chiral molecules generically corresponds to a superposition of the two chiral structures rather than just to one or the other. And this stable state is taken to be the complete description of the molecule. The second condition is also satisfied because the state described by quantum mechanics will evolve in accordance to the time-dependent Schrödinger equation. And then in reality, we will only observe a left or right-handed structure of the examined molecule. Also, in the case of resultant Hamiltonians, we can see that this is a special case of the measurement problem because the eigenfunctions of the resultant Hamiltonian are taken to be a complete description in Modlin's sense, despite the fact that the ground state corresponds to a state with no identifiable structure. The second statement is also straightforwardly satisfied. And of course, the third one as well, because we observe particular molecules with a specific isomeric structure and not a superposition of those structures. Now, I don't want to say that any of this is new, right? I'm not purporting to make any huge scientific achievement here. All of this has been said before, especially in the scientific literature. With respect to Hund's paradox, this is hardly a revelation. It has already been pointed out. And even with respect to resultant Hamiltonians, philosophers and scientists alike acknowledge the relevance of foundational problems in quantum mechanics. Yet they take the novelty here to lie in clearly identifying the connections of the two problems as special cases of the measurement problem, especially with respect to the second one, right? So with the explaining the inability of resultant Hamiltonians to identify structure. And also the novelty lies in showing how putative solutions to the measurement problem can be possible ways out of existing philosophical conundrums about chemistry, and especially with respect to the persistent problem around chemistry's relation to quantum mechanics. And this brings me to the last section of my talk, the implications of all this to philosophical problems around chemistry. So I want to present these implications in the context of each of the three realist putative solutions to the measurement problem. So you can see more clearly how this can affect our views on chemistry's relation to quantum mechanics. So let's start first with the Everett interpretation. So according to modern versions of the Everett interpretation, when environmental or measurement device degrees of freedom become entangled with a quantum system, the wave function does not collapse. If the quantum system is in a superposition in the measurement basis, then the measurement device will enter into superposition as well. Now, if the coherence is as the Everettians suppose, then within a very short time period after interaction, interference between branches will be suppressed, and each branch instantiates approximately independent worlds, right? So here are the two problems, Hund's paradox and the inability of resultant Hamiltonians to identify structure, are resolved by the Everett interpretation by acknowledging that our fundamental symmetric quantum mechanical description determines a superposition of structures for isolated molecules. But when it comes to macroscopic observers, they will never come into contact with all the branches of the superpositions, but only with one of the branches of those, thus seeing one specific structure, right? So this is because macroscopic observers inhabit effectively non-overlapping worlds, and this is and this explains why we see only one structure and not a superposition of those. Now, how is this relevant to questions about chemistry's molecules and molecular structure? Well, if we literally take the Everett interpretation, then it follows that isolated molecules are in superpositions of different atomic configurations. And since these interpretations are here interpreted physically, when the system is in a superposition of different arrangements, there is no determinate molecular structure. Thus, a system in superposition of, say, right and left-handed enantiomers, in fact, does not have a determinate handedness. And likewise, if we consider more generally isomers that are in the superposition of different molecular structures, if the system is in a superposition of different molecular structures which correspond to the same resultant Hamiltonian, then the system again does not have a determinate molecular structure. Now, this is very interesting from a chemical perspective, because this means that the type of molecule a chemist is kind of familiar with does not exist in the isolated context, so pre-measurement, right? Because the isolated molecule the chemist takes into account does not have the determinate structure in isolation. So we shouldn't be looking at molecular structure when we consider molecules in isolation. And this has interesting metaphysical implications as well, because this perhaps should prompt us about thinking of the nature of molecular structure, not as an intrinsic property, which is usually kind of implicitly assumed from a chemical perspective, but rather as a relational property. And given how important molecular structure is in identifying and distinguishing between different types of molecules, maybe this suggests that it doesn't even make sense to look for chemistry's molecules in isolation in the first place. And this is because structure forms such an important part in the identity of molecules in chemistry. Of course, this also has implications for chemistry's relation to quantum mechanics. So in the Everett interpretation, molecular structure is derivable. For each world, the observed structure of that world will correspond to some branch of the superposition of molecular configurations described by the resultant Hamiltonian. Now, if we consider the system in isolation, if there is no molecular structure in isolation, then importantly, there is nothing to be reduced. So the purported failure of quantum mechanics to find and identify the structure of a molecule is not a failure of reduction, because in this case, there is nothing to be found, right? And to be reduced in the first place. So the argument, the anti-reductionist argument is in this sense undermined. Now, if we are to consider the molecule in contact with an environment, then in the Everett interpretation, structure is reducible. And this is because the Everettian claims that the coherence effects follow from an application of the Schrödinger equation. Of course, this doesn't necessarily mean that we have to accept a reductionist view straight ahead, because even within the Everett interpretation, there are available emergentist views regarding classicality. But again, here we see that how the debate on chemistry's relation to quantum mechanics shifts and becomes now contingent on the particular interpretation of quantum mechanics that we assume. And I think that's the most important thing, right? Now let's go to another possible candidate to solve the measurement problem, which is the de Broglie-Bohm theory. So here the theory posits a dualist ontology where a configuration of particles with determinate positions is guided by the wave function known as the pilot wave. Quantum systems wave functions are in real physical superpositions here, and particles always have determinate positions. Now, the interesting thing here about thinking of molecules and molecular structure is that one might think that given that the particles here always have determinate position, there is a molecular structure in isolation in accordance to this theory. However, it is misleading to think that this structure in isolation is in any way similar to that we understand by chemistry. And this is because when there is interference between branches, the practical trajectories can be utterly non-classical. So even though in isolations particles have determinate positions, they are not organized in structures that chemists would recognize. So again here, one could claim that there is no structure in the chemical sense of structure to be found in isolation. And this in turn undermines anti-reductionist claims because there is no chemical structure to be found in isolation, right? So there is no purported failure of reduction either. Now, of course, one might question more generally the reductionist credentials of the de Broglie-Bohm theory with regard to other aspects of this theory, right? So including the status of the wave function and the role of decoherence. However, if we accept that insofar as the measurement problem resolves, insofar as the de Broglie-Bohm theory resolves the measurement problem in a reductionist way, then this also allows for the reduction of molecular structure. So again, here we see that the discussion of chemistry's relation to quantum mechanics and shifts in the context and becomes contingent on the particular interpretation of quantum mechanics that one assumes. And I'll give one last example with respect to spontaneous collapse theories. So here, spontaneous collapse theories resolve the measurement problem by positing a spontaneous stochastic physical process, which collapses wave functions in superpositions of position onto approximate eigenstates of position. Here, Modelin's trilemma becomes consistent because we deny statement 2. So the Schrödinger dynamics are occasionally interrupted by spontaneous collapses, which break the symmetry between the branches of the superposition, right? So here again, returning to the identity of molecules, whenever there is a superposition involving different isomers, that superposition is with high probability maintained until it becomes entangled with a large enough system whose spontaneous collapse will likely occur. And prior to that, there is no determinate molecular structure in isolation. There will be in relative isolation superpositions of a variety of different structures. So again, similarly to the Everett interpretation, since there is no molecular structure in isolation here, the question of reduction, the question of whether we can reduce molecular structure becomes moot before collapse onto a particular molecular structure has occurred. Now, insofar as sufficient collapses take place, there is a well-defined molecular structure, which is consequent on the dynamical localizations of the wave function. And again, here, one could debate about whether spontaneous collapse theories imply or support a reductionist or emergentist view. But again, we see how the discussion again shifts in the context of a particular interpretation of quantum mechanics. Now, let me go to the conclusions. So what are the lessons that I'd like to draw from all this? The first lesson is that the views on persistent philosophical problems about chemistry can be greatly informed by close examination of the measurement problem and its putative solutions. So until now, chemistry's relation to quantum mechanics has been considered largely independently of the interpretation one assumes to quantum mechanics. So philosophers of chemists would be mostly neutral about that, as if this plays no role to the question, right? Which I believe is wrong, because depending on which sort of interpretation one assumes, this also is going to affect how we're going to view and support chemistry's relation to quantum mechanics. And this becomes evident by the fact that if we go and look closer at some of the putative solutions, some of the anti-reductionist claims are now undermined, and reduction becomes a viable option. And this also brings forward another important lesson, in my opinion, which has to do with the importance of distinguishing molecules that are in isolation from those that are not. So it seems that we need to revise our intuitions about molecules in isolation. And it might be the case that it is nonsensical to look for chemical entities and properties when those systems are in isolation. And of course, this also shows that we need to reframe the debate on chemistry's reduction, because prior to this, it has been mostly assumed that whatever chemical properties we see in non-isolation, we should expect those properties to exist in isolated context as well, which, however, according to quantum mechanics and the measurement problem, doesn't seem to be the case. Now, of course, this is not the end of the story, and there are a lot of things to continue investigating and thinking about. And obviously, I've already mentioned some of them. So first of all, solutions to the measurement problem do not necessarily imply reduction. However, as I said before, now the question is reframed. The question of chemistry reduction is reframed and becomes contingent on a particular interpretation. And there's also an interesting question about the identity of molecules. Given how important molecular structure is in identifying and distinguishing between different types of molecules, if molecular structure is non-existent in isolated contexts, then it may not make even sense to talk about molecules in the chemical kind of sense of the term when we think of those systems in isolated settings. And of course, a more metaphysical kind of question, or another metaphysical question, has to do also with the nature of chemical properties, because then it seems it would be incorrect to think of molecular structure as an intrinsic property of molecules that is independent of them interacting with their environment. So that's the end of my talk. Thank you very much. I haven't put full references, but this is the work that I've based most of my talk, and there you can find all the references that I've used here. Thank you.
Thank you, Vanessa. That was wonderful. All right, so we finished a little early, so we have extra time for questions right now. There has been a robust discussion happening in the chat window. If anyone would like to elevate questions or comments from the chat window to audible vocalized questions, that would be very much appreciated. I see a hand from David Chalmers. Go ahead.
Yeah, I just got a very naive question about this. I thought some of the problems of quantum chemistry were about whether quantum mechanics can predict the results of certain observations of molecular structure. Now, if there were problems of that kind, then I guess that wouldn't be an issue about the measurement problem, because problems about measurement are part of the empirical apparatus, which is prior to the measurement problems. You're saying that actually none of the main big problems of explaining molecular structure in terms of quantum mechanics are problems of explaining observations of molecular structure?
No, of course not. Look, the objections against quantum mechanics' inability to kind of describe structure are varied, right? And sometimes you can find them muddled in between in-principle worries and practical worries. So the practical worries would be the ones that you mentioned, that quantum mechanics cannot predict some of the chemical properties. But those seem not to be as, and of course, I suppose these warrant a different sort of response, and the measurement problem wouldn't be able to accommodate an answer. Nevertheless, I take that the in-principle worries that are mentioned, which have to do with the putative inability of quantum mechanics to even identify some structure, are accommodated by the measurement problem, by thinking of it.
Thanks. So there's a bit of a competition between how questions are listed in the participants window and also comments that showed up in the chat. The first person to raise a question in the chat was Logan. So hopefully it's okay. I go with Logan and then Simon and then, yeah. So Logan, do you want to go ahead?
Yeah, thanks. It was really a great talk. It was really incredibly stimulating. I think, so I'm actually gonna jump off on a tangent, which is not directly related to the discussion that's going on in the chat, which was a lot focused on chiral molecules and superpositions. But I think related to that, so there's the ammonia molecule, which is famously a pyramid structure with a nitrogen at the center and 3 hydrogens forming a pyramid, a trigonal pyramid. We know that actually is the ground state of that is actually a superposition of the 2 structures. And you can actually measure famously a microwave transition between those 2. But in addition, when you actually go to higher pressures, that microwave transition shifts frequency and eventually disappears. And what that means is, at least my interpretation is, that the eigenstates of the ammonia molecule in isolation are different from the eigenstates measured by spectroscopy, right? So this is an experimental measurement, different from the eigenstates of the ammonia molecule in the environment, and as you increase the pressure, what you see is that the eigenstates of ammonia molecule in environment of other ammonia molecules actually become localized. That you actually, so that the and it's actually a gradual process, as you might expect for any process of decoherence, right? So that in the limit where the ammonia molecule is totally isolated, the ground state is in fact a superposition of the two interlocked trigonal pyramids. But as you increase the pressure and the ammonia molecule starts interacting with its environment, then the eigenstates localize, and eventually they become sort of totally localized. And that transition, the microwave transition, is the transition between the symmetric and anti-symmetric superpositions of those two states. And that transition eventually disappears, which you can measure experimentally. And I'll just say that I think one of the things that I love about your talk is it really kind of suggests that that studying a molecule in isolation is not chemistry, it's physics. And I know that seems silly, but like, I mean, like when I go into a chemistry lab, I'm using, 10 to the 23rd molecules, and they're definitely not in isolation. So, I wonder to what extent, sort of bringing the environment here can help. That essentially that the eigenstates of what you write as the resultant Hamiltonian are always assuming a molecule in isolation. And perhaps if you include the environment, perhaps then actually the eigenstates then become something that look more familiar to what we have in chemistry. And I don't know, ammonia is one example where you can really see that transition, and it's theoretically very well explained, but I don't know if there are other examples. Sorry for a long.
If I could have just a quick finger on that, Logan. To what extent is thermal radiation also important for decoherence when it comes to questions about molecular structure and stability of configurations? Because you're talking about pressure in terms of just having lots and lots of molecules bumping up against each other. But I know that Simon had mentioned in the chat a question about the role of thermal radiation in decoherence. To what degree does that matter, and for any particular systems?
I mean, I'm sure that matters, and as someone mentioned in the chat that probably if you have radiation, of course, chiral molecules will absorb right or left-handed polarized radiation oppositely. So there is obviously interaction with radiation as well.
Right. I think Elise pointed that out. Elise, I think, pointed that out in the chat. Great.
So should I say something about all this, or?
Please do if you'd like.
So I'm very happy about these questions, because I totally agree with Logan. And actually, in our paper with Alex, we talk about Hund's paradox, the resultant Hamiltonians, and then we have a third case study, which is about ammonia. Because in Anderson's paper, more is different, this is extensively examined, right? The inversion of the ammonia molecule. And we argue that this is also a case of the measurement, a special case of the measurement problem. I just didn't have, the reason why I didn't add this today was that surprisingly, such cases aren't mentioned in the discussion of chemistry's relation to quantum mechanics. So I wanted more to focus on that part of the debate, rather than more generally how all this comes down to the measurement problem. But I totally agree with you on that. And the other thing that you said, that in isolation, chemistry becomes irrelevant. I really agree with that. You're absolutely right. And it's often assumed that the things chemists, because if you go to standard definitions or classifications, even if you look at the periodic table, right, and you see the elements, you assume that chemists refer to elements in isolation. But they do not refer to it. None of this is experimentally identified or measured in isolation. And even, standard properties that are considered as intrinsic of molecules are properties that are measured when those molecules interact with other ones around. And if you measure, for example, the structure of molecules, it vastly changes, for example, with respect to thermodynamic conditions in which you think of them, right? So if you look at if you say the particular structure of a X molecule, that structure is always contingent on the thermodynamic conditions and in the substance in which, or rather the general environment in which it is experimentally examined. So I agree with everything you said.
Great, thanks. So the next question I have is from Simon.
Yeah, thank you, Vanessa. I love the talk. I agreed with almost everything, the issues you were raising and so forth. Though I was a little bit puzzled about the molecule identity question, but perhaps you'll come to that. But I did feel that in a way, the thrust of your talk would have been even more effective had it been directed at the attempts to solve the measurement problem coming from the direction of chemistry. Because surely every attempt to solve the measurement problem that is driven by realist concerns has to be responsive to what is going on at molecular reality as studied in chemistry and non-equilibrium statistical mechanics more generally. So it's a wonderful test case for different approaches to the problem of measurement or solutions. And in particular, take dynamical collapse. I mean, I think if dynamical collapse is really unadulterated with any add-ons, perhaps these regimes will be no different from the Everett interpretation. So that's one sort of question. And I think very salient here as well, insofar as decoherence is being driven unitarily, how does it connect with the kind of stochasticity that is going on by virtue of the spontaneous collapse mechanism? So, I mean, that's a very interesting interaction there between those different sets of ideas. If it's adulterated collapse theory, so it's added, I don't know, it has a flash ontology or something like that. I mean, how does it stand up? I mean, my question to you is, take the flash ontology in GRW. I know that's only one of several collapse theories, but does it give a remotely adequate account of a chemical and biochemical reality?
Yes, that's interesting. I don't know. This is still this is very much a work in progress, right? And it's a bit tricky because from the chemistry perspective, the evidence of chemistry seems to be accommodated. I don't see how chemistry itself can give you an answer as to which of the interpretation one should prefer, because chemistry by definition looks at all of these after a measurement, right? So how can you kind of accommodate, how can you explain, how can you provide support to any of those interpretations through chemistry? I'm not so sure how you can do that by recourse only to chemistry, right? And what we know about chemical molecules.
Yes, but as we were just discussing, we're agreed, of course, chemistry turns into physics. We're looking at actual phenomenology of physical chemistry. Now, when you're looking at that phenomenology and actually how we study it in given laboratory environments, this is physics. And the question is the adequacy of various approaches to the measurement problem to do justice to that phenomenology.
Yeah, that's true. I don't know. Sure, I don't know, to be honest.
I mean, just to be a little more focused upon it, suppose you can do it fine in pilot wave theory, but it's entirely at the level of structures in the wave function. There is almost nothing in the corpuscles and the trajectories that is connecting with the biochemistry. It's entirely in the structure of the wave function. So that then would be fuel to the view that the corpuscles are epiphenomenal and are playing no role when it comes to physics. I mean, that's just another illustration, is it not? So this is something that all three, it seems to me, major interpretations are going to have to be answerable to this kind of stuff.
Yes, definitely. This is something that I need to think about and work on more, to be honest. But I think there's a lot that you can cash out of this. I never thought how chemistry can be informative of this to the philosophy of physics. I more thought of it the other way around, given the kind of persistent dead ends that philosophers would reach about chemistry. But that's a very interesting approach as well, I suppose. Now, about the identity of molecules that you mentioned before, I have to say that this is something that also is a work in progress, because this is the part that I'd like to continue from this project. But it also has to do a lot with metaphysics here, and to what extent structure is a key feature of the identity of molecules, and if so, then the question comes up about whether molecules and their identity is undermined by the lack of an identifiable structure as well. I don't know if that answers your question, but I just wanted to say that.
Well, I very much wait to hear more. I mean, I've worked quite a lot on distinguishability and how it feeds through into emergence of discernibility. So I'd be very interested if you've got problems that can't be solved. Anyway, thank you. I've taken up too many questions already.
Thank you so much. So the order I have now is Aurelian and Sebastian and Arkadiusz. Aurelian?
Oh, okay. So you can hear me? Yes? Yes, okay. So thank you for your very nice talk. My remark is about what was discussed in the chat, the role of decoherence, about photons, for example, interacting with molecules will break, generally create some super selection rules and will break superposition very quickly. Unfortunately, it's very, very fast. And you have to do at a very low temperature to check kind of superposition of molecular states in a configuration superposition, for example. But it has been done for some very, very specific states with the atom. For example, the group of Haroche was able to do that with the superposition of Reinberg states of atoms. But for molecules, it's so difficult because the decoherence time is maybe smaller than 10 to the minus 12 second or maybe minus 20 second. But this doesn't change anything about the fact that you have two questions, because you have the decoherence process is about the wave interacting with waves, so all photons interacting with molecules. But you need indeed to distinguish this problem from the ontology, and then it's very important in your, I think, to say that, for example, if you consider the ontology like the Broglie-Bohm theory of Brownian mechanics, you have to definitely define the trajectory, and you believe that you have one defined configuration, even though your wave function can be very complicated. So this is for me, these two questions have to be distinguished very clearly in the discussion.
Yes, I agree, and it's apologies if that wasn't clear here. So for me, the coherence is kind of the means that shows you that the mechanism with which you do collapse and you break the superposition, right? But it doesn't explain itself the need to break the superposition in the first place, right? And this is why existing replies, and this is why, yes, existing replies to these problems and to the use of the Bristol Hamiltonians aren't sufficient in terms of decoherence, because decoherence doesn't identify the core issue here, which is the fact that we have these problems in the first place due to the measurement problem. Now, of course, decoherence is going to explain the mechanism with which we break the symmetry, but we need an in principle reason why we're put in that position in the first place, which we lack in this discussion. And this is the thing that I wanted to focus on here.
I agree completely with you. With what you say, it's interesting to distinguish these two issues, because I think all interpretations are neutral concerning the notion of decoherence. The decoherence is here all the time, but we have to take it into account necessarily because it's part of Schrödinger equation. But if we need to say the molecule is this or that, then we need to make something more define an interpretation.
For me, the question here is not so much to decide which particular structure is rather, I'm not looking for a specific, I'm not proposing a specific mechanism that will be able to predict which particular structure we observe or not, but rather explaining the in-principle problem of needing such a mechanism in the first place, right? But, yeah.
All right, thanks everybody. So due to time constraints, we're gonna have to pause this discussion here. I've written down the remaining people who have questions, and they'll be able to go at the beginning of the list when we do our final hour after the 3 talks. So I'm going to stop the recording now.